This is Bernard Paulson. We will now discuss the material in Chapter 9 of this book. This is perhaps the most mathematical portion of the text, as we will look at regulation, both from an analysis standpoint and simulation standpoint. First, say a few things about regulation. So most processes inside a cell are heavily regulated, and what regulation basically comes down to is a number of chemical reactions that involve molecules that modify the rates of various reactions inside the cell. This particular slide shows 4 levels of regulation of enzymes. First, there is the regulation of transcription and translation, namely the determination of how much protein is made. Very often, enzymes as molecules exist in 2 different forms, active and inactive. In this case, in this slide, the inactive enzyme needs to be phosphorylated before it becomes active. Enzymes can be phosphorylated and dephosphorylated by protein kinases and protein phosphatases. The active enzyme itself is then subject to binding of ligands to the enzyme, coenzymes, prosthetic groups, divalent ions, and so forth. Then, of course, the substrates and the cofactors, simply their concentration, helps determine the rate of reaction that actually takes place. So you see that regulation in biology is complicated and can involve most of the major processes in a cell. The biology, the biochemistry, the genetics of this is quite complicated, and you can take an entire class or many classes actually if you wish to study this subject. Here we will focus on how to describe the regulation of enzymes mathematically inside a network. The first thing I will discuss is the phenomenology of regulation and signaling and how we think about the key concepts from a systems point of view. I will then go through a few simple cases that are amenable to mathematical analysis, and this analysis brings out some of the underlying principles. In most cases, it is impossible to carry out such analysis, and we can approach the understanding of regulation by simulation. In this case, the enzymes are explicitly described as molecules in the network, and so are the many states of the enzyme as characterized by regulators being bound to it. We will see the importance of fractional states, namely, if we have a pool of enzyme, what fraction of it is in an active state and what fraction of it is in an inhibited state, as an example. We will also see the big difference between monomeric, dimeric, and tetrameric enzymes in terms of their efficacy to exert regulatory effects on metabolic pathways. First, we'll discuss some of the basic principles. 4 of them are shown in this slide. First, Regulation has a built-in bias. It activates a process, we often designate that with a plus, or it inhibits a process, and we will designate that with a minus. Second, there is an active range over which the effect of a regulator are felt. In the diagram there, we show a curve, an S-shaped decaying curve, similar to that of Hill kinetics. And in the steepest part of that curve, when it decays the most rapid, the reaction rate is the most sensitive to the concentration of the inhibitor. If the inhibitor is outside of the active range, then changes in its concentration do not affect the reaction rate much. The third concept is the gain. And the gain is related to how much the reaction rate changes in response to a change in the inhibitor. This can be expressed as the derivative of the reaction rate with respect to the concentration of the inhibitor. And that is shown in the graph. The fourth concept is the issue of local versus distant location. Often, regulation is exerted by a compound on the reactions that flow into or out of the node that compound represents in a network. That would be local regulation. A distant regulation is shown in the second blue box, where a compound Y will affect the reaction rate degrading X, and Y is located far away from X in the network. Of course, physically, they are located nearby one another inside the cell, but there will be many, many links apart in the network. We will first analyze regulation and look at some of the mathematics associated with regulation of enzyme activity. We will begin by looking at local regulation. In fact, the only treatment mathematically here is of local regulation. There are 5 basic cases we need to look at, and that is the unregulated case, that is just simply governed by mass action kinetics, as conveyed by the stoichiometric scaffold. Feedback inhibition is a circumstance in which the compound will inhibit its rate of formation. So as the concentration of X builds up, the rate that forms it will go down. Feedback activation is the opposite. If the concentration of the compound builds up, then the rate of formation is stimulated by that higher concentration of X. Then we have feed-forward inhibition. That means that X will inhibit its degradation, and we will have feed-forward activation, in which case X accelerates its degradation. So we have a basic mass action kinetic scaffold that underlies all reaction networks, and then layered on top of that will be these regulatory rates that modify the intrinsic mass action kinetic nature of a reaction network. All right, now we're going to have to do some mathematics. So in equation 9.1, we show the network that we're interested in. Of course, it is trivially simple. A single node and 2 links, one going in and one going out. The dynamic mass balance is shown in equation 9.2, where the time derivative of X is simply the rate of formation minus the rate of its degradation. This equation can be linearized, and linearization is very important in the analysis of regulatory effects. And the linearization of the equation represented in 9.2 is shown in 9.3. I have a prime on x now. X prime is a deviation variable. It is equal to x minus x at the reference state where the linearization is carried out. That reference state is essentially always the steady state. Now you see I have the derivative of V1 and V2 appearing in the reaction rate. And the combination of these two is represented by the quantity lambda. Lambda, of course, will be the eigenvalue of the system. And now you may want to refresh your memory on eigenvalues from your linear algebra class. So we have a situation here where the regulation is local. We have a dynamic mass balance. We have this eigenvalue. The sign on the eigenvalue is the bias, whether we're going up or down. And the gain is the magnitude of lambda. Let's look at this graphically. So in the unregulated situation, we have the rate of formation, V1, being insensitive to the concentration of X that is represented here on the X-axis, and the rates clearly on the Y-axis. We show V2 as a linear reaction rate that is such that V2 is linearly related to the concentration of X. If I look at the eigenvalue in this case, lambda, the derivative of V1 with respect to X will be 0. And of course the derivative of V2 with respect to X is just going to be a constant. There is the steady state where the two interact, and the eigenvalue associated with this system when it's unregulated is designated by lambda star. In the case of feedback activation, the reaction rate V1 will actually now increase with the concentration of X. The derivative of V1 with respect to X will be a positive number, and if I look at the eigenvalue now, it will be a positive number minus another number that is slightly larger. So in absolute magnitude, lambda will become smaller. Lambda star will be a negative number, and lambda in this case is still a negative number, but is a smaller negative number. In the case of feedback inhibition, the curve for V1 will be decaying, and the derivative of V1 with respect to X will be a negative number. Now when I calculate the eigenvalue, I will have a negative number minus the other derivative. So now the value of lambda is more negative than of lambda star. And for the feed-forward regulation, we have similar situations. If you have a positive feed-forward regulation, then V2 is a more steeply increasing curve with the concentration of X, and the derivative may now be larger. And in the case of feed-forward inhibition, the derivative of V2 with respect to X will become smaller, and the eigenvalue moves correspondingly relative to lambda star. So the more negative an eigenvalue is, the more quickly the system will return to a steady state when perturbed. So when lambda with the regulation becomes more negative than lambda star, you have stabilization, and vice versa. So for local regulation, this leads to a simple principle. Local negative feedback supports the mass action trend, whereas local positive feedback will counteract the mass action trend. And any signals locally that counteract the mass action trend are actually destabilizing, whereas the control signals that support the mass action trend tend to be stabilizing. We can now look at this in more detail and consider the inhibited case, the feedback inhibited case, where V1 will be a decaying function in X. And we're going to go back to Hill kinetics and pick that particular rate law for V1 as shown here. And the degree of cooperativity is 2. And therefore I have that second power in the denominator. V1, the turnover rate, is just linear in X. I can now substitute these two into my dynamic mass balance, and now I have a complete differential equation that will describe my dynamics. The first thing I need to do is to find the steady state, and that is when the two rates are equal. And if I do that and rearrange the equation I had on the former slide, I get this cubic equation that will give me the steady state. Note that in it, X is always divided by the equilibrium constant K, and I can introduce a dimensionless concentration chi relative to K. Please remember that when X is close to K, that's when the curve is decaying very steeply. And as we discussed in chapter 5, very often you have physiological concentrations close to their K values. And if that were the case here, that would be close to maximum responsiveness of the regulation. If I introduce this dimensionless variable in there, my cubic equation looks a lot more simpler, as shown in equation 911. You can solve this equation analytically, and the solution is shown in 912. The parameter A that appears in this equation is dimensionless, and what it tells us is shown at the bottom of the slide. It is the ratio of the natural turnover of the system, the time scale for the natural turnover, to the time scale associated with regulation. For regulation to be effective, you would expect it to act more quickly than the natural turnover, and therefore A would be expected to be a number greater than unity. We can now compute the steady state as a function of A, and that is shown in this slide over here. And as A increases, the steady state concentration increases. I can also calculate lambda simply by evaluating the derivatives and varying the number A. And as expected, lambda becomes more and more negative as the inhibition becomes tighter, which is represented by A, and principally when A exceeds unity. I can now simulate, and this simulation here shows the dimensionless concentration chi, and I'm just plotting it here relative to the steady state, so I can plot many curves on the same plot. So if the y-axis is 1, that means I'm at the steady state. These simulations show a drop in the initial concentration by 10%, and I show 3 response curves here with increasing values of A. So as A becomes a larger number, the eigenvalue becomes more negative, and you see that the response is sped up. So if you have Hill kinetics for feedback inhibition, you can characterize it by this dimensionless number A, and the smaller A is, the larger A is, especially relative to unity, the more effective this regulation is in terms of speeding up the response of the concentration of X as it's perturbed. So that's relatively simple. The next thing we're going to look at is activation. So in this case, V1 is no longer a constant, but increases with the value of X. And now we can pull out a mathematical expression from V1 from chapter 5. That is the version of the Hill-Rate law where we have an activator, which in this case is X. Again, I can substitute in V1 and V2 into the dynamic mass balance and get equation 917, and I can in fact represent that with the dimensionless concentration chi as shown. Interesting things happen in this case. So V1 is increasing like this, as shown here with X, an S-shaped curve. Now I draw three different straight lines that corresponds to V2 with different turnover values, different numerical values, different turnover rates of X. And you see here that I can have intersections between these curves that are either such that there is one intersection or three. For some values of K that give me the slope of that curve, I can have three intersections and therefore three steady states. And it turns out that two of these are dynamically stable and one is dynamically unstable. Stability of a steady state means that if you perturb the system a little bit away from that steady state, it'll return to it, whereas an unstable steady state is one that when a system is perturbed in that steady state, it will actually run away from it. And you can readily see, for instance, the steady state is such that the stable steady state is such that if I perturb the concentration of X above that steady state, then the drainage rate is faster than the formation rate, and it'll return back to its steady state. In the unstable steady state, the opposite is the case, and therefore it is unstable. You need to think about this for a few minutes before you understand it. Let's try to figure out for what values of K, the turnover rate, I can have steady states. So I see that there will be two critical values of K where the curve for V2 will just touch the curve for V1, and that can happen in two different ways as shown in this slide. And if the numerical value of K is such that I am between these two curves shown, V2 plus and V2 minus, I'll have multiple steady states. If I'm outside, I will have a unique steady state. So how can we evaluate this? Let me first observe that at the point, at these two black points shown in this graph, V2 just touches V1, and it turns out that the slope of these two curves is going to be identical at that point. V2 is like the derivative of V1 at that point. We also have the steady state that has to be satisfied there, and when the derivative of V2 is equal to that of V1, the eigenvalue is 0. So if I want to find the conditions, these critical conditions that demark the difference between unique and multiple steady states, I'm going to have to solve these two equations simultaneously. I have to find the steady state, which is any intersection between these two curves, and I want to find those particular states where lambda is also 0. And those are the two black dots shown in the lower curve. This slide is interesting and requires some thought if you are seeing it for the first time. Now, it turns out that I can actually, in this case, analytically solve these equations simultaneously. That is the steady state equation and the equation where lambda is 0. Here's my equation for lambda. I can just evaluate the derivatives, and there it is. And I can actually combine it with the steady state equation. And by using this variable transformation there, z equal to chi to the nth power, and the degree of cooperativity nu does not have to be 2 here, like we had in the case for the inhibition analyzed a few slides ago. So we can combine these two equations, the eigenvalue being 0 and the steady state, into one quadratic equation. And if this equation has real roots, that means that I can satisfy the other two equations with a real number for the concentration and therefore have multiple steady states. And again, you need to think about this for a few minutes before you fully grasp it. I can show this situation graphically. So in panel A of this figure, I'm showing the parameter space. I have two parameters here, alpha and A. A I introduced earlier, and alpha is the acceleration ratio for the activation, introduced in chapter 5. The two curves shown in this plot are the two critical conditions I graphically illustrated 2 slides ago. So in between those two curves, I can have the number 3 for the number of steady states. Above or below it, I have a unique steady state. Now let's see how this is actually manifested. So let's look at panel B. So in panel B, I fix alpha at a numerical value of 10, and I calculate A as a function of the steady state concentration. And you see that that is a curve that goes up to the point labeled II and then drops until it reaches this point I, and then it increases again. And remember that this is all within the criteria of these two equations being satisfied. Let's look at panel C. In this case, I fix alpha at a value of 0.03, and I calculate across the dashed horizontal line in panel A. Here I find 2 points designated by III and an IV. These points are shown again in panel C. If you look in between them, and if I were to draw a horizontal line in between them and pick a value of alpha of say 6, you can see that I can have 3 steady state concentrations that correspond to that value of alpha. So if I'm above that first dashed line, I have 1 steady state. If I'm below the second dashed line, horizontal dashed line, I have 1 steady state. But if I am in between, I can have 3 steady states. Panel D shows a dynamic simulation where I start out at the red point in the parameter space in panel A, where alpha is 0.3 and A is 0.3 and alpha is 10. At time 0, I change my A value to 0.1, as also shown in panel A. And the response to that is for the concentration to go from a high steady state to a low steady state. Note that in this case, lambda is 0, and therefore this is an eigenvalue that lies in the origin of the complex plane. Let me conclude this section of the lecture by talking a little bit about the importance of the location of the eigenvalues in the complex plane. If the eigenvalues are real and negative, the dynamic response will be as shown in this slide, just an exponential decay. If they move off the real line and become slightly imaginary, that's the situation where you can have an overshoot, as shown with the green curve. If they migrate further off the real axis, you can have multiple overshoots or damped oscillation. And if you have purely imaginary eigenvalues, you will have sustained oscillations. And so these cases correspond to the first 4 cases in the table below. And as you recall, this is a table that I had in lecture 2 when I told you that the characteristics of the transient response could be many, and the first 4 in this case are related to the location of the eigenvalues in the complex plane. And as I said earlier, you need to look at your linear algebra text. These will be the eigenvalues of the Jacobian matrix that is formed when you linearize the equations. What I treated in this lecture so far was a one-dimensional system, so there is no Jacobian. It's simply a one-dimensional equation that has one eigenvalue in it. So let me just conclude that I could add into that complex plane image to the top left a dot in the origin, and a dot in the origin would mean the occurrence of multiple steady states, as shown with the example that I just went through. So we have some observations here. First, I'll say that the regulation moves the eigenvalues around in the complex plane. The mass action scaffold will have eigenvalues located on the negative real axis, and regulation can move them around. The negative feedback inhibition we talked about will move the eigenvalue down the real axis to the left, so it becomes more and more negative. The positive feedback will move it to the right, and it can crawl up all the way to the origin in the complex plane, where you will have the onset of multiple steady states. The eigenvalues are systemic time constants, so the more negative they are, the more faster the response. The mathematics needed to analyze regulation is complicated. In listening to me talk through the mathematics in the previous slide, you might think that that is a complex situation, but you might just imagine how complicated they can become as I start to treat more complicated systems than the one I did so far in this lecture. I should state again that local feedback inhibition, or equivalently local feed-forward activation, is stabilizing. It makes the real part of the eigenvalue more negative. The opposite is true for local feedback activation or feed-forward inhibition. Those signals tend to be destabilizing because the real part of the eigenvalue becomes more positive. And again, if it hits the origin, you can actually bifurcate the steady state into multiple different solutions. So that concludes the discussion about the analysis of regulation. We are now going to look at more complicated regulatory phenomena through the use of simulation. This is a control loop that I'm going to talk about for the rest of the lecture. On the left, I may have some primary pathway like glycolysis or the pentose pathway that has the compound X as an intermediate. As you know, X may not be completely degraded to CO2 and energy, but siphoned off through a biosynthetic pathway to make a product that is needed for cell growth or protein synthesis. And we might think of this pathway, this biosynthetic pathway leading to X5 as a biosynthetic pathway for, say, an amino acid. And X1 could be, for instance, erythrose 4-phosphate, an intermediate in the pentose pathway. So some of the X1 is being siphoned off to make X5 that in turn is being used in protein synthesis. What I'm going to do is I'm going to put this system into a steady state for chosen parameter values. Then I'm going to perturb the input flux B1 of X. And the control system here should prevent that perturbation from propagating into the biosynthetic pathway and just lead to X1 being processed through V0 and out of the network that I've defined here. And the way that regulation takes place is that the enzyme that I'm going to call X6 here, that catalyzes the first reaction into the biosynthetic pathway, has a regulatory site. And X5 can bind to that regulatory site, as shown, reversibly. And if X5 is bound to the regulatory site on X6, you have an association of X5 and X6 that I'm going to call X7. And this is an inactive form of the enzyme. And that is indicated by this square. So the circle and the square here are used to denote the active and inactive form of the enzyme. I use this also when discussing the symmetry model in chapter 5. So as the concentration of X builds up, more and more of the X6 is moved to the X7 form. And if the concentration of that enzyme goes down, then the flux V1 will go down. So this is an example of negative feedback inhibition. As X5 builds up, it'll feedback inhibit the rate of its own formation. This is, of course, something that we frequently see in biochemistry textbooks. Here, we are going to study the dynamic consequences of this regulatory interaction. And note that this is regulation at a distance in the network, unlike the local regulatory phenomena we looked at in the first half of this lecture. Okay, so we take out our toolbox and we formulate the dynamic mass balances, and that is pretty straightforward here. We had the time derivatives equal to the fluxes going in and out of every node, and then we put elementary mass action kinetic expressions in for every one of these fluxes. And you write this out as shown in this slide. The last two equations you see are equal and opposite. It's minus V6 and 6. And if you sum these two up, these equations up, you will get the time derivative of a sum of X6 and X7 to be 0. That's of course a statement of the fact that the total enzyme concentration is a constant. The enzyme is either found in the active or the inactive form. And very often we are interested in the fraction of the enzyme that's in the active form. So this is a pool, this is a time invariant, and X6 is the part of the pool that carries out the catalysis. So we are interested in knowing what fraction of the overall enzyme is in the active form. And that'll be the fraction shown there, and it'll vary between 0 and 1. When it's 0, there's no active enzyme. When it's 1, all of the enzyme is active. Okay, so we need to first find the steady state. The steady state, of course, is where we're going to start our simulation, and then we're going to perturb that steady state and see how well our regulatory mechanism will reject the disturbance that we are going to impose on the system. Steady state equations are, of course, generated by putting all the time derivatives to 0. And in this particular case, all these steady state equations, all 6 of them, can be combined into one simple quadratic equation that we can solve. There are two dimensionless parameters here, A and B, that determine what the steady state is. You can also find these by simply numerically solving these 6 equations. There will be another way of doing it, and a third way of doing it would be to integrate the differential equations out to a very, very long time until it reaches a steady state. So there are 3 ways in which you can find the steady state. Analytically, as happened to be possible here, number 2 numerically, or number 3 by simulation to very long times. Whichever way you choose, you now have values for the concentrations that when put into the differential equations will give you zeros for the time derivatives, and you're in the steady state. Okay, so let's simulate here. There is a skeleton representation of these 2 pathways, the primary pathway and the side pathway. I'm going to bump the input to x1 by 10-fold. So this is a serious disturbance. And now I'm going to simulate, and what I get in response to that are the concentrations changing over time and the fluxes changing over time. And the numerical values that I use are shown in the slide. This is very complicated and hard to see what is going on. But briefly, you can see that when I dump more x1 into the system, x1 builds up. And if you look at the flux diagram, V0 that drains it also builds up. But you also see that as x1, as the concentration of x1 builds up, the reaction into the biosynthetic pathway, V1, also shoots up just by virtue of mass action. And then V2 goes up, then V3, V4, and eventually V5. As V4 goes up, you see on the concentration side that X5 starts to increase. And as X5 starts to increase, it starts binding to X6, and X6 starts dropping. And now the inhibited form, X7, starts building up. And you see on the flux diagram that V6, the equilibrium reaction between the enzyme and the inhibitor, gets active for a while and then goes back to 0 as it goes to a new equilibrium state. Eventually, you see all the fluxes in the side branch become equal as you reach the steady state at something like 0.3. So that is the reaction. Very complicated reactions, many concentrations changing, 7 of them, and 6 fluxes changing. But what is really going on here? What I can do is I can form very simple phase planes or phase portraits that help me understand what's going on. And I'm showing 2 of them here. What I am showing in panel A is the flux into the biosynthetic reaction, is biosynthetic pathway, and the flux out of it, V1 and V5. And of course, they have to be equal and opposite in the steady state. In the beginning, at time 0, I start out on that steady state line at a value of something like 0.06. As I dump x1 into the system, V1 will shoot out. So it'll move rapidly horizontally across the phase portrait, because V5 hasn't increased yet at all. It's just V1. But over time, that disturbance percolates down that pathway, and X5, the end product, starts building up, and that feedback now inhibits V1, so V1 will start to drop. and it drops, and you move, and the system now moves towards the 45-degree line, overshoots it, but then finally settles down on it at time infinity. And you see that the fluxes at time infinity are much higher than at time zero. So this system could not reject this disturbance. It took that biosynthetic pathway from a low flux to a high flux. It was not uncontrolled and just took on any value, but the regulation did respond to this disturbance, but not really well. So that's what we learned by looking at the fluxes. Okay, so that's the flux balancing on the biosynthetic pathway. The next plot I want to look at is the state of the enzyme. What was the state at the enzyme? If I look at this phase plane, I'm plotting the free enzyme or the active enzyme on the x-axis and the inhibited form of the enzyme on the y-axis. And because the sum is a constant, I will have to travel up and down a line here that has a slope of -1. If I have no inhibition, everything is in the form of x6, and if I have full inhibition, everything is in the form of x7, and I have full inhibition of the system. In this case, for the parameter values chosen at t equal to 0, about 65% or so looks like of the enzyme is in the active state, and therefore about 35% or so are in the inhibited state. The reaction to this disturbance is such that the state of the enzyme becomes more inhibited, and it moves to the point where about maybe 0.25 or something like that, about 25% of the enzyme is active and 75% or so is inhibited. So that's what this regulatory system really does. It moves the enzyme from the active state to the inactive state. But in this particular case, it really doesn't do it so well because the flux through the pathway is much higher after the disturbance than before. The lower slide here emphasizes the fact that the fractions we can calculate, for instance, on the y-axis in this case, would be the fraction inhibited, and on the x-axis I would have the fraction of the enzyme in the free form or the active form. So these two diagrams really tell me what I need to know. It gives me the flux state of the input and the output of the biosynthetic pathway and where it settles down and how I swing away from that steady state. And the lower diagram tells me how effectively I'm sequestering the enzyme in an inactive state. Now, I'm going to look at a couple of variations of this system, this regulatory system, to try to improve it. The first one I'm going to look at is regulation by X5 of the rate of synthesis of the enzyme. So now X5 is actually going to go in and reduce the amount of enzyme in the system. And that's shown in that little box, red box to the upper right. So the rate of translation or enzyme synthesis is V7, and that's going to be inhibited now by X5. And all enzymes have a natural turnover that is indicated by V8, which is a decay. So for any given concentration of X5, there will be a translation rate or a synthesis rate of the enzyme, and that's going to be matched by the decay rate. This is inhibition of a gene expression or protein synthesis, and this is a very common regulatory mechanism. I should say right away that the dynamics of this regulation are much slower than the dynamics associated with regulation of the activity of the enzyme. So now we got to expand our model a little bit, and the differential equation for X6 now has two additional terms in it, V7 and V8, as shown in equation 947. I will now no longer have a mass balance on the enzyme because it's synthesized and degraded, and X6 plus X7 do not necessarily have to equate to a constant. So the rate loss I'm going to use here is just the first order turnover rate for the decay of the enzyme for V8. And for the inhibition, I'm going to pick, for illustrative purposes, a Hill form of the inhibition, where I pick the degree of cooperativity to be 1. And that's shown at the bottom of this slide. Now I can simulate my system again. Now I have a bi-level or 2 layers of regulation. I have regulation of the activity of the enzyme, and I have regulation of the total amount of the enzyme. The dynamic responses look very similar on the short time scale as those that I showed before. So I'm just focusing here on the longer time scale, and this is the time scale above 5 to 10 time units. And you see in this case, for the first 5 units or so, the total amount of the enzyme is relatively a constant, but after that you see a decay in the total amount of the enzyme as the regulation of the translation becomes active. That becomes inhibited, and that leads to a drop in the total amount of the enzyme. And you see the concentrations of X1 and X5 drift slowly or mildly on that longer time scale. We also see in the panel to the right that V7 and V8 are now active, and V7 drops very rapidly, and then V8 drops following that because the concentration of the enzyme drops, and V8 is proportional to that. And you see it takes a long time for these two to come into balance, which happens maybe at 80 time units or so. And during this time, V1, the flux we are trying to regulate, keeps going down. So we show here the fast metabolic inhibition and the slow response associated with the regulation of the total amount of protein. Now let's look at the 2 phase planes that I introduced us to earlier. Now they look slightly different. The graph on top looks similar to my previous version, where V1, in response to the disturbance, shoots out along the horizontal axis, and as the concentration of the inhibitor X5 builds up, that starts going down, and I move towards the steady state line. I overshoot it, but now I don't go straight to it as before, but I start migrating down the steady state line towards the initial state, but I don't make it all the way there. Now I end up at a flux a little bit below 0.3, looks like. On the lower, so that's my flux phase portrait. I can look at now at the state of the enzyme. You see that the reaction here is similar as to that before, when the fraction of the active state of the enzyme starts dropping along the minus 45 degree line. But in this case, the total amount of enzyme drops to about 0.6 relative to the total inventory in the beginning, because of the inhibition of the rate of protein synthesis. And you see at time infinity, I end up with a total sum of about 0.59. So here I see my 2 different regulatory responses. A rapid one that changes the flux or the activity, changes the activity of the regulated enzyme and the flux through V1, followed by a slower response which reduces the amount of the enzyme that catalyzes V1. This is still an unsatisfactory regulation because the system still settles quite far away from the original steady state. It's a little better, but I could not reject the disturbance entirely. The second perturbation I'm going to look at, or the second, I should say, modification of the system that I'm going to look at, is to consider more complicated versions of the regulated enzyme. I'm not going to consider regulation of the protein synthesis, but I'm going to look at more stringent inhibition of the activity of the enzyme. And as we saw in chapter 5, regulatory enzymes can be dimers or tetramers, as shown in here. So now I need to add more binding steps for the inhibitor to the enzyme. So here I have X5 binding to X6 as before to form X7. But now there will be two binding sites on the enzyme. So X7 can now bind to a second molecule of the inhibitor X5 to form X8. So X8 would correspond to the two filled black circles to the left, X7 would correspond to the one filled black circle, and X6 would correspond to the two open circles. So now there are three states of these enzymes. Both active sites open, one active site open, and neither active site open. Well, I should say not active site open, but one of the sites of inhibition occupied by the inhibitor, and two of the inhibition sites occupied by the inhibitor. In the lower part of the slide, I show the same thing for a tetramer, where I can now have the enzyme in 5 different states. All 4 sites for the inhibitor unbound, 1 bound, 2 bound, 3 bound, and all 4 of them bound. And this tetramer therefore goes further and further into an inhibited state as the concentration of X5 builds up. So that's the dimer, and that's the tetramer. So there are more chemical reactions involved in here, but the overall state of the enzyme is either active or inactive. It's just that the inactive form of it has more and more inhibitors bound to it. So now let's simulate these responses. I'm going to simulate the response to the same disturbance as before. Now I see that the reaction of my system is quite different. This is the same phase plane as before, where I have V1, the flux into the network, plotted against V5, the flux out of the biosynthetic pathway. The response of the monomer is the same as I showed before. This is when I was considering only one site on the enzyme that can bind to an inhibitor. If it is a dimer, you see the response is better, and if I have a tetramer, it's better yet. So the disturbance rejection in this case is best for the tetramer, slightly worse for the dimer, and much worse for the monomer. And in fact, you can see the tetramer gets close to rejecting the disturbance entirely. If you were now to combine the tetrameric form of the regulatory enzyme with the regulation of protein synthesis, you would get very close to the original steady state in response to this disturbance. The combination of these two effects are left as a homework problem in the text. So we're going to make some observations here. Enzymes can be added explicitly as molecules into simulation models. Enzymes can have multiple functional states, as illustrated by the dimer and the tetramer, and the active and the inactive state, and so forth. The fractional state is important. So if I have a finite pool of an enzyme, what fraction is active and what fraction is inactive is very important. And tetramers have more effective regulatory characteristics than dimers, and dimers more than monomers. This may help us perhaps understand why tetramers are so, why regulatory enzymes are so commonly tetramers. So let's summarize this rather difficult lecture. The activities of gene products, such as enzymes, are often regulated. Phenomenologically, regulation is described by its bias, activation or inhibition. is described by the concentration range over which a regulatory molecule is active, and is also regulated by the strength of the regulation, what we call gain in control theory. In addition, the distance in the network is important. We distinguish between local regulation and regulation at a distance. And again, distance here isn't physical distance, because these reactions can be taking place quite closely in space, but the distance means how many links in the network the regulator is from the reaction it's regulating. In general, for local signals, we showed the principle that regulation that supports the natural mass action trends in the stoichiometric scaffolds are stabilizing, and those that don't tend to be destabilizing. Regulation of enzyme activity comes down to regulating the functional state of the enzyme, which is typically fast, and then regulating the amount of the enzyme that is present, and that's typically slow. And it is useful to examine its functional state as stated before. We've now seen that in simulation models that regulatory mechanisms can be built on top of the basic stoichiometric structure of a network, and it is described by basic chemical events, namely the reactions that move the regulated enzyme from one state to the next. This lecture concludes part 2 of the text. This part introduced us to methods to evaluate and estimate the numerical values of the rate constants that we need. It introduced us to the stoichiometric scaffold and some of its basic properties. And it introduced us to the important process of regulation, which are processes put on top of the basic stoichiometric scaffold to modify its dynamic responses. And I emphasize that those regulatory events are described by chemical equations, chemical transformations, and they can simply be added into a simulation model by their explicit description. We will now move on to part 3 of this class, where we look at actual biochemical pathways and build simulation models for them. Thank you for your attention.